All right, so in this podcast, we're going to learn about something called a net ionic equation. And this is just going to help us finish out that last little part of page 8 that we didn't do in class underneath our solubility rules, and does kind of build on that idea. You're also going to need that periodic table that we wrote all over and edited to make sure that you can tell if something is soluble or insoluble, because that is where we're going to be starting with this idea. So let's look at it. We've got some instructions here that are evidently going to help us write net ionic equations. And I know it looks like a lot, but if you actually kind of skim over it, what you see here is that each of these steps is really instructions on how to write a different type of equation. So in the end, our whole goal is to get to a net ionic equation where we are isolating the solid. So this is going to be a precipitation reaction, and the net ionic equation is going to show the solid and the ions formed or used to make it. And that's it. We're going to leave out all of the spectator ions, meaning things that weren't used, that weren't changing before my reaction to after. They were just sitting around watching. So the net ionic equation, when it comes down to it, is kind of the important part of our overall precipitation reaction. It's just the focused reaction. So all of the stuff that we're doing here is going to be getting us to this focused reaction. And I know it might seem like a lot, but as we get more and more used to these details, really all you're going to need to remember is kind of what order we go through them in. You always start with a balanced equation, then we're going to turn that into what we call an overall ionic equation, and then use that to create our net ionic equation and identify our spectator ions. So let's get into a few more of these details. Here I've highlighted some of the important points about what we're supposed to be doing in each of these steps. That first step is kind of the same old that we did back in Unit 7, write and balance a chemical equation. And then we're going to take that balanced equation and rewrite everything in that equation that is aqueous broken up into ions. So basically step 1 is put ions together into these compounds that it says that we are mixing, and then step 2 is to break them all right back up again, but only the aqueous things. Now, it is going to be important that we keep our states of matter there. Anything that started aqueous is still going to be aqueous even after we break it up. And because we're turning things into ions, we're going to need to see the charges on our atoms. But it should be easy to find those because we already found them and identified them when we were writing and balancing the equation. So if we kind of keep track of our work and kind of show our work as we're doing step 1, it'll help us with step 2. Now, I'll explain this a little bit more when we see an example, but we're going to be changing subscripts that are on elements into coefficients if our element isn't part of a polyatomic ion. So it's just showing that full breakup of that compound, and I'll kind of explain that, like I said, when we look at an example, it'll make more sense. So, overall ionic equation is basically bust everything up, break it all apart. This is going to be the biggest, longest part of this process. But then we're going to look at that the overall ionic equation and find the solid, the one thing we didn't break up. And then on the reactant side, we're going to find the ions used to make it. And those are the only things we're going to keep and rewrite as part of our net ionic equation. And once again, we need to keep those states of matter and keep those ions charges written on them. But they were already written on them up here, so we just have to remember to keep writing them, keep them with our pieces. And basically, at this point, we're splitting the overall ionic equation into 2 parts. The important stuff that makes the solid and its ions come into our net ionic equation, and anything from that overall ionic equation that was not coming into our net ionic is what we call the spectator. Like I said, they're not doing anything, they're not forming our solid, they're just sitting around and watching. So that is our process. And so I want to give a few more little details just in case, there was details about every other step, But I know some of you might need a quick recap over, well, how do I write and balance an equation? And I'll show you and walk through these processes when we are doing that first example at the bottom together. But if you want to take a quick second to write some of these notes off to the side, if you've forgotten, this would probably be the time to do it. So whenever we write and balance a chemical equation back in Unit 7, you always need to check your charges. These are all basically going to be ionic compounds in these net ionic equations. So we're going to be checking charges and cross-dropping reducing in order to form nice stable compounds. Now, it's generally only going to give you the stuff that mixes together, the reactants. So we're going to have to predict our products according to our double replacement rules. Just remembering that the first element from the first compound gets together with the second element from the second compound when we form our products. And if I get the second element from the first compound and the first element from the second compound, we always have one of the first elements, one of the second elements, because those are positives and negatives. We make sure to keep that first element, the positive one, at the beginning. So B is still at the beginning, but now it's with X instead of Y. So we can form our compounds by following this general pattern. And then, of course, to get our states of matter and to decide what's going to be breaking up in the next step, we're going to have to use the solubility chart that's on the back of the periodic table. Anything that's soluble is aqueous. Anything that is insoluble is going to be marked as a solid. So that should be a solid foundation to build off of. So let's look at our first example. It's already written out for you. So I'm not going to write a whole lot, but I will kind of point out where each of these steps we just talked about happened. So in the question, it said to write all of these things that when potassium sulfate and barium nitrate are combined. So when I see potassium sulfate and barium nitrate, I start trying to write their equations, their formulas. I'm just going to kind of do that above them here. You can kind of show this off to the side if you want. Potassium is K plus 1, sulfate is S minus 2, barium is plus 2, and nitrate is minus 1. Make sure to keep an eye out for these 8s and ites. Those are signs that those are groups from the back of our periodic table on that polyatomic list. So because I had that plus 1 and minus 2 here, those cross-dropped reduced to make K2SO4. Then plus 2 and minus 1 came together to give us barium nitrate with 2 nitrates there. Then as I was predicting my products, I took K and NO3 and made one of my products. Doesn't have to always be the first one. And then I took my other two products, barium and sulfate, and put them together to make my BaSO4. And this time it was kind of nice because my K and my NO3 were plus 1 and minus 1, so I just needed to shove them together, no extra numbers. And same with Ba and SO4, plus 2 and minus 2 means that they're happy and stable together, just like that. So we get all of our formulas written, and then we can go back and check our groups on the back of the periodic table. And remember, if this is a precipitation reaction, and generally that's what they're going to ask for a net ionic with, both of your reactants should be aqueous to start with. We really just need to focus on finding which, if any, of our products is a solid. So that's our writing and balancing the chemical equation. The balanced equation is our first step. And then if you look at this, we took each of these groups, K2SO4, and in our overall ionic, we broke them back up into K plus 1 and SO4 minus 2. And this is where I mentioned that anything that was a subscript is going to turn into a coefficient as long as it's not on one of my polyatomics. So here I have a 2 and a 4 in K2SO4. Those are my subscripts. And the 4 was part of sulfate. So we're not moving that, not doing anything with that. That just becomes SO4 minus 2. But because that 2 was not part of a polyatomic. It wasn't part of our original ion. When we break up this compound, what that's saying is that I needed 2 of these Ks and 1 of these SO4s coming together. So we're going to break it up to show those pieces. I have 2 separate Ks coming off of my 1 SO4. So we never break up or change those polyatomic groups from the back of the periodic table. They start and end their life as a group, no matter what. But if I have a subscript on another element, or even over here, I have a subscript on the outside of my nitrate, then I do bring that 2 to the front. I make it a coefficient because this 2 is not part of that polyatomic. So just breaking up everything that's aqueous, showing their charges again, just like what we saw before, and just moving subscripts to be coefficients. Notice I did not break up my BaSO4 because it is a solid, not aqueous. Let's clean this up a little bit, because now all that's left is to write our net ionic and our spectator ions, and that's all going to be part of this overall ionic. That's why we take that step to find it there, because all that we're going to be doing is focusing on the one thing we didn't break up, barium sulfate, and the ions that were needed in order to create it, barium and sulfate. And we just pull all of that stuff down with their charges and their states of matter into the net ionic equation. And anything else that was left behind, and you'll notice it's the same stuff on both sides, those are our spectator ions. And it doesn't really matter how many we have or really what states, they're always going to be aqueous. So we just need to list them out and show that these are spectators. They're not really part of the reaction, they're just there. They were helping support our K and our Ba. Our K and NO3 were supporting the Ba and SO4 when things were initially mixed, so that they could come together and form that barium sulfate. So that is this example. Let's go ahead and do one for ourselves and go through this process together. So I am going to make a little bit more room here since I needed that on the last one anyway. And this tells us that solutions of silver acetate and strontium chloride are combined. And evidently it wants us to go through this whole process here. On a test or a quiz, it will be very clear when it wants you to do this whole big long process. And so I'm going to start by finding my ions. Silver is Ag, it's always a +1. Acetate is C2H3O2 with a -1 charge. Strontium has a +2 charge. Chlorine, which is just normal chloride, is a -1. So as we start trying to write our formulas, I have a +1 and a -1 here. So that's just going to become Ag C2H3O2. I'm going to leave a space for my state of matter. I'll come back and do that later. My +2 and my -1 here, when I cross drop reduce, is going to form SrCl2. And now I need to start predicting my products. And I'm just going to take the first thing from my first compound, mix it with the second thing from my second compound, after remembering to leave a space for my state of matter. Those things always seem to take up more space than I imagine, so I like to leave their spaces there. So we're going to be putting Ag and Cl together. And then our leftover pieces here are going to be strontium and acetate coming together, and this I am going to have to cross my +2 charge over onto my acetate. So this is going to be Sr and then parentheses C2H3O2. State of matter. Okay, now if we go back and check, luckily, like I expect, both of my original compounds are aqueous. Chlorides are almost all aqueous, and strontium's not an exception. And acetate is always aqueous. If I check Cl, as I was checking it over here, I noticed that Ag was one of its exceptions. So it tends to be soluble, but when it's with silver, it's not. So this right here is my solid, my precipitate. And then I did notice that acetate is aqueous all the time, no exceptions. So that is aqueous on the product side as well. All right, balanced equation. Oh, wait, it's not balanced. That's important. Let's see. I have one Ag on both sides. I have one acetate here and two there, though. So I am going to have to come back and put a 2 in front here, which means I'm going to have to put a 2 in front there to keep my Ags equal. One Sr on both sides. That looks good. Then 2 Cls and 2 Cls. Okay. That's all I need to be balanced. So now let's go ahead and turn this into our overall ionic equation. And we're going to do that by breaking up everything that's aqueous. So everything but my silver chloride. And it is important that I keep this 2 with both of my pieces, because it means I do have 2 silvers and 2 acetates here. So let's do it. I have 2 Ag plus 1s aqueous and 2, not Cl this time, C2H3O2 negative 1s, also aqueous. And then I just have 1 Sr plus 2 ion. And this is where I'm going to bring my 2 subscript up to be a coefficient, because each of those chlorines are going to break off separately. And then thank goodness I can stop breaking things up. It saves me a little bit of space here. And then I can just write this as Sr plus 2. And my little 2 must have disappeared at some point in there. And I can bring that little 2 up front to make this 2 C2H3O2 negatives. Ooh, just barely fit it. Like I said, this is the longest part, which is why I tried to start as far over on my screen as possible. So now I'm going to key in on my solid, 2AgCl solid, and I'm going to find the pieces, my ions on the reactant side that made it, and those are going to be my net ionic equation pieces. So I'm bringing 2 Ag plus 1 aqueous and 2 Cl negative 1 aqueous, and this is forming 2 AgCl molecules that are solids. And everything else that I see here, those acetate and strontium ions, those are our spectators. That's it. So a little bit of writing, but it's really not that bad of a process, especially if you know how to write your equations and compound formulas still. We still need those skills, and so that's going to pay off. If you don't have those skills, especially predicting products, come in and work with me on it. Write those notes down. At this point, if there was anything you didn't understand, circle it, highlight it, come to class with questions, or go back to those instruction slides and see if I had any instructions there that would help you with it. But let me know what I can do to help.